Now that we've mastered how to write electron configurations, the last little bit to learn is drawing your orbital notation arrows. It's not honestly much harder than the electron configurations. Just think of it as adding in one extra detail that tells us how the electron's spin is. Okay, so your criteria for success for today is to be able to apply the off-ball principle, Paulie exclusion principle, and Hund's rule in order to draw orbital notations. You won't have to draw them today. You just have to be able to answer the 4-question exit ticket at the end. If I were you, I'd go ahead and open it up on Google Classroom, just so you can at least look at the questions and see what information you should be looking for, or so you can follow along and answer them. But if you want, you can watch the video and then go save them and answer them at the end. So let's get started. You can now write a configuration for any element on this periodic table. You know to start at 1s, read left to right, and draw 1s2, 2s2, 2p6, and so on. That address or configuration tells us the location or the probability of where that electron is within that atom. What the orbital configuration will do is just tell us what the spin on that electron is. Why we have to do this is because electrons are always moving around these orbits. They're always moving, okay? But we just need to have an idea of where could it possibly be? What's the highest chance it could be here versus here? And then what could the spin more than likely be? You have learned, or I should say, in order to make orbital configurations easier, instead of drawing out the boxes every time, we really just start at 1s and proceed all the way through. It stays in this order and must remain in this order every single time. You have already learned and mastered the off-ball rule. This just says you need to feel your lowest orbital first. You always start at hydrogen, or always start with 1s. Now it's time that we're going to take these next 2 rules, or the last 2 rules, and kind of tie them in with the off-ball principle that you've used in order to write your configurations. Paulie exclusion rule says your electrons are always opposite and paired. Each orbital, or yeah, I can say orbital, holds a pair, so holds 2 electrons, but they must have opposite spins. If the first electron has an upward spin, then the second must spin down. So just the quick saying for Paulie is just opposite and paired. Opposite spins, and then they each hold 2 electrons. And then the last rule that you must remember, Hund's rule told us that we like to have the same arrows, or the arrows with as many as the same spin as possible. The way you apply this rule is you always fill the up arrows first. So if I was filling in, let's say I was filling in for oxygen. Oxygen is 2p4. It ends in 2p4. So those arrows that I would draw for oxygen would actually go 1, 2, 3. I fill my up arrows first, and then I would go in and fill my 4th arrow down. So this shows you I have the most arrows with the same spin. I have 3 up arrows compared to the 1 downward arrow, instead of it being split with 2 up arrows and 2 down arrows. All right, so just to show you again, if I was doing 2p5, 2p4 for oxygen, I would fill my up arrows first, and then I would go through and fill my downward arrows. So orbital notation is the same, like I said, as configuration. Your s orbital can still only hold 2 electrons. Your p orbital can still hold up to 6. Your d still is 10, and your f orbital is still up to 14. So now let's practice. Again, if I was doing this for carbon, the first step would be to write out your electron configuration. Okay, that's what we have here. 1s2, 2s2, 2p2. Now, we draw the number of electrons, or I should say, when we write the orbitals, you want to write a shell for all of your electrons. That is why you see a 1 line under the 1s, 1 line under the 2s, and then 3 under the p, because each orbital can hold 2. So that means s only has 2, so it just needs the 1 line. So if I go through and I was to draw my configuration for carbon, this is how I would do it. Carbon has 6 arrows. You must fill the lowest orbital first. You must remember that your electrons are opposite and paired. And if you have more than 2, you draw your up arrows first. So carbon, here's 1, 2, 3, 4, 5, 6. And I will be finished. Most of you probably think that, or are wondering, why did I not draw this arrow here? It fits the first rule of lowest energy level first. It fits the second rule of opposite and paired, but it does not fit the third rule of the most spins of the same as possible, okay? If I were to draw it this way, we're even. 3 up spins, 3 downward spins. We don't want that. If we can have majority of our spins be the same, that is what we want. So that's why, like I said, if you have more than 1 line, you draw all your up arrows first. All right, second example, chlorine. You first have to ask yourself, how many electrons does chlorine have? Look at your periodic table, find the atomic number. That tells you the number of chlorines. I'm gonna wait about 3 seconds for you to locate the atomic number of chlorine and tell me how many electrons there are. All right, the atomic number is 17. Therefore, we have 17 electrons. Therefore, we have 17 arrows or 17 electrons to place. If it helps, you can write out the configuration for chlorine here. 1s2, 2s2, 2p6, 3s2, 3p5. Writing out the configuration isn't mandatory, but it does help you kind of understand at least where your arrows should go. So now, let me draw that configuration on my orbital filling diagram. I have 17 to go. Lowest orbital first, opposite and paired, as many with the same as possible, so fill your up arrows first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Just to double check that my orbital matches my configuration that I wrote here, I add up my exponents. 2, 4, 10, 12, 17. All right. I believe we have one more example. I'll walk you through one more. Yeah, and after this example, I want you to try this one on paper. So pause the video right here, try it on paper, and then press play and see if you get what I get. All right? So lithium, I'm gonna wait. You should hit pause right here. Hit pause. Write it out in your paper. Hit pause, hit pause. Go ahead. I know you didn't hit it. I'm gonna wait, hit pause. Okay. Lithium. First, we have to figure out how many electrons it has. 3 electrons. How do I know? Because the atomic number is 3. So that means I have 3 that I must place. If it helps, again, write out the configuration for lithium. 1s2, 2s1. So now let me place my arrows. Up arrow, down arrow, there's 2, up arrow. Double check my work, 2 in the 1s, 1 in the 2s. I started with the lowest possible, I have them opposite and paired, and then I have as many with the same spin as possible. I have 2 up with the same up spin. All right, that is the end of our intro for the first day. At this time, you are going to complete your exit ticket. Your exit ticket is on Google Classroom. If you need any help, please feel free to private message your teacher. It's only 4 questions. Rewind the video if you're stuck. If you don't get a score you like the first time, go back in and you get a second attempt. And then we'll average the scores and put those into the grade book. I hope this was a decent try for today. We'll talk about how it goes and see if we want to put more videos in class. See you guys tomorrow.